Hello class, we're going to do a little Lewis structure practice today. In the last video we saw how the way that atoms bond according to their relative electronegativities influence the way they behave and the way that we draw them in a Lewis structure. Let's go back to the beginning idea of what a Lewis structure is. It's an attempt to represent the bonding between atoms in a molecule. The way that we represent that helps us understand better how these molecules will interact with other molecules, either in solutions or in chemical reactions. So let's take a look at one of these molecules that we did yesterday. We're going to revisit ammonia here, NH3. So like all non-hydrogen atoms, except for maybe helium and lithium, nitrogen is trying to get an octet. It wishes to behave like a noble gas. Remember, octa means 8. Noble gases, except for helium, have 8 valence electrons. That's the maximum stability in nature in the electron cloud in that outer valence shell. So nitrogen has 5 electrons, okay? We know that you can't represent more than 2 electrons as a pair, and we assume that we have 3 unpaired ones. Nitrogen, in all cases, when it forms a compound, will gain 3 covalent bonds. So naturally, it makes sense that we have 3 hydrogens, each one of which has an electron ready to help. So let's decide what type of bonding we're looking at when we bring these 3 hydrogens in to provide these 3 electron pairs to give nitrogen its noble gas stability. So we can see that if you look at your Pauling chart on page 308, you should see that nitrogen is one of the more electronegative elements. So let's go take a look here. And we can see here that nitrogen has an electronegativity rating of 3.04. Hydrogen, however, is about 2.20. So if we take a look at the electronegativity difference, this is a pretty polar molecule. This means that it's probably going to interact well with water. It does dissolve in water. And it's not going to interact so much with nonpolar substances like fats, oils, and waxes. So we can assume that for each of these hydrogen bonds that are going to happen, that we're going to have dipole symbols, which are our basic symbols for polar bonds. So I'll be color coding here. So hydrogen is basically going to provide a single covalent bond here. We just replace these 2 dots with a line. We have one here, and then we have one here, okay? And at each of these bonding sites, we can put dipole symbols, indicating that we have a fairly large electronegativity difference between nitrogen and the hydrogens. Now, one thing that I want to call your attention to is this unbonded electron pair. This is an important thing in helping us understand molecules. Molecules that have these unbonded electron pairs on the outside, which frequently oxygen and nitrogen do, tend to produce somewhat more dipole interactive polar bonds. So that's a pattern that we're going to be looking at more as we move along here. But for now, let's just take a look at how we got our Lewis structure to work out. We started off with 5 valence electrons because nitrogen is in group 13, as is phosphorus and arsenic. He has 5 outer valence shell electrons, thus he needs 3 bonds to get his octet. Each one of these hydrogens always has only 1 electron, so there we go. And this is very much a polar molecule. So another reason that this is polar, not just because we have dipole symbols, but also when we have that outer electron pair that is unbonded, that often sets up a certain amount of a charge imbalance in itself, and that is another indicator often of polar bonding. So we're going to take a look at these three others, and in